Every time your laptop fans kick on, you're hearing the sound of wasted energy. In our current world, moving data means moving electrical charge, and that creates friction, or what engineers call resistance. But in 2026, researchers at the Norwegian University of Science and Technology, or NTNU, discovered a way to bypass this friction entirely. They found it hidden within a specific alloy of niobium and rhenium. This isn't just a better wire, it's a fundamental shift in physics. It uses something called triplet superconductivity to carry information using the spin of an electron rather than its movement.
To understand why this is so special, we have to look at how normal superconductors work. Usually, electrons pair up in a singlet state. They spin in opposite directions, canceling each other out. While these pairs can move without resistance, they are effectively blind to magnetism. Because their spins cancel out, they can't carry a magnetic signal, which is how we store and process most of our data. The NbRe Discovery changes the game because it creates triplet pairs. Here, the electrons spin in the same direction. This means they can carry a magnetic spin while still being superconductors.
Think of it like a highway. Standard electricity is like a crowd of people pushing through a narrow hallway, bumping into walls and creating heat. Standard superconductors are like a smooth ice rink where people slide in pairs. But triplet superconductors are like those same skaters carrying a spinning baton. They aren't just moving, they are carrying a specific orientation that can be used as a signal. This is the holy grail of condensed matter physics. It allows us to combine the speed of magnetism with the efficiency of superconductivity in a single material, niobium, rhenium.
The team at NTNU used advanced spectroscopic techniques to prove these triplet pairs existed. They observed a spin current, a flow of magnetism without any net flow of charge. This was previously thought to be incredibly difficult to achieve in a stable alloy. Most triplet superconductors are fragile and only exist at temperatures near absolute zero, but NbRe showed surprising resilience. By carefully tuning the ratio of niobium to rhenium, the researchers created a non-centrosymmetric structure. This fancy term just means the crystal lattice is lopsided, which forces the electrons into that rare triplet state. This discovery isn't just a lab curiosity, it's the foundation for a new type of hardware called Spintronics. Instead of using electricity to flip bits, we use the spin of the electron itself. And because these triplet pairs move without resistance, the chip doesn't get hot. Imagine a data center that doesn't need cooling towers, or a phone that stays cold even while rendering the most complex games. The potential is staggering, but the real genius lies in how we actually build machines out of this magic metal, and that is where the engineering gets truly clever.
To understand how an NbRe chip works, we have to rethink the bit. In a normal computer, a 1 is a burst of electrons, and a 0 is the absence of them, but moving those electrons takes work. In a spintronic system, the electrons don't need to move from point A to point B. Instead, we just flip their spin. It's like a line of people holding flags. To send a signal, they just flip the flag up or down. Because the electrons in our NbRe triplet pairs are already aligned, they act as a perfect medium for these spin waves. The signal travels through the material like a ripple on a pond.
The genius of the NTNU discovery is that NbRe allows these spin waves to travel much further than in any other material. Usually, spin signals die out after just a few nanometers, a problem called spin relaxation. In NbRe, the triplet pairs protect the spin. Because the electrons are locked together in a superconducting state, their spin orientation is shielded from the noise of the surrounding atoms. This means we can build spin valves, the spintronic equivalent of a transistor, that are incredibly small and efficient. These valves control the flow of spin current with almost zero energy input.
Here is how the valve works. It uses 2 layers of magnetic material with the NbRe alloy in the middle. If the magnets are aligned, the spin current flows freely. If they are opposite, the current is blocked. This is called giant magnetoresistance, but in a triplet superconductor, it happens with zero heat. We are essentially using magnetism to switch a superconducting current on and off. This allows for clock speeds that would melt a traditional silicon chip. We're talking about processors that can run at terahertz frequencies, thousands of times faster than today's best hardware. But it's not just about speed, it's about density. Because there's no heat, we can stack these spin valves into massive 3D structures without worrying about the middle layers melting. Current chips are mostly 2D because heat needs to escape from the surface, but an NbRe processor could be a solid cube of logic, packed with more computing power than an entire modern server farm. This opens the door to truly brain-like computing, where billions of connections can exist in a tiny space, all firing simultaneously without a single watt of energy being wasted as heat.
The transition from electronics to spintronics is as big as the transition from vacuum tubes to the transistor. It's a fundamental rewrite of how we manipulate the universe to do math. And the best part? It uses materials we already know how to handle. Niobium and rhenium are well understood in the aerospace industry. We just had to figure out how to mix them for the digital age. But making this work in a lab is one thing. Making it work in your pocket, that requires solving some of the toughest material science challenges of the century.
Niobium rhenium is a remarkable alloy, but it's not easy to work with. To get that triplet state, the ratio of the two metals has to be perfect, down to the individual atom. If the mixture is off by even a fraction of a percent, the non-centrosymmetric structure collapses, and the material reverts to a boring standard superconductor that can't carry spin. Engineers at NTNU solved this by using a process called magnetron sputtering. They blast a target with plasma, causing atoms to fly off and land on a surface in a perfectly controlled thin film.
The next challenge is temperature. While NbRe is more resilient than other triplet superconductors, it still needs to be cold to work. The goal is to raise its critical temperature to something manageable. By adding tiny amounts of other elements, a process called doping, engineers are trying to stiffen the crystal lattice, allowing the triplet pairs to survive at higher and higher temperatures. We aren't at room temperature yet, but for data centers, even liquid nitrogen temperatures would be a massive win. Nitrogen is cheap, and the energy saved by the chip's efficiency far outweighs the cost of cooling.
Then there's the interface problem. Our current computers use electrons and copper wires. How do you connect a spin current chip to a charge current world? The solution is a spin injector. It's a specialized layer that converts moving electrons into a polarized spin stream. It's like a turnstile that only lets people through if they are spinning in the right direction. This allows us to build hybrid chips using standard silicone for simple tasks and NbRe Spintronics for the heavy lifting, like AI processing or complex simulations. The implications of this are hard to overstate. Right now, the biggest limit on AI isn't software, it's the power bill. Training a massive model takes enough electricity to power a small city. With NbRe Spintronics, that power requirement could drop by 99%. We could fit the power of a supercomputer into a device that runs on a watch battery. This isn't just about making things faster, it's about making them sustainable. It's the first real path toward a digital world that doesn't demand a constant, massive sacrifice of energy. Next time you feel your phone getting warm in your hand, remember that we are living in the heat age of computing. But thanks to the work at NTNU and the strange physics of NbRe, that age is coming to an end. We are standing on the edge of the spin age, a world of silent, cold, and impossibly fast machines that work with the fundamental green of the universe rather than fighting against it. The discovery of triplet superconductivity in niobium rhenium is more than just a breakthrough in material science. It's the key to a future where our technology is as efficient as the laws of physics allow.